Okay, this is the next video in the series on the October 23 paper taken in Edexcel International Physics A-level exams. So I'm going through this for my own students and I'm putting it up here for you to use as you will. Okay, so this next question is question 19. And question 19 is really simply about resolving, this time with momentum and velocity vectors involved. Obviously, momentum is mass times velocity. So you need to know the equation for momentum to solve this equation. So curling is a sport played on ice. You may have seen this on TV before. If you have, I think it's an Olympic sport. Players slide stones made of granite along ice. Okay, the photograph shows two of these stones. Okay, each stone has the same mass of 19.1 kilograms. So they're giving us the mass, and it says a player slides a stone at a velocity of 1.70 meters per second towards a stationary stone, as shown. Okay, so this is the view from above. So this stone is going forwards, going to glance off the stationary stone and create the situation that we're going to analyze now. The stones collide. After the collision, both stones move off as shown below. So the angles are given. Okay, and after, you can see that the one stone goes off at 50 degrees and they're giving you the new velocity, which is obviously lower because it's going to lose some of its momentum to the stationary stone, and that moves off at an angle of 30 degrees with an unknown velocity v. Okay, so they want us to show that the unknown velocity v is about 1.3 meters per second. So the way I like to do it, or the way I've chosen to do this question, is to simply show that vertically, so looking at it initially, there was no vertical motion. Yeah, so that means up and down on the page. Initially, all the velocity was horizontal, so going across from left to right. So if we look at up and down, there was no velocity upwards and no velocity downwards. So at the end, when this one goes off at an angle 50 degrees to the horizontal, it has a vertical component or an upwards component in the diagram, and that's what we're going to use. And the stationary stone is now going to move downwards on the page at an angle of 30 degrees to the horizontal. So if we can resolve the momentum in terms of vertical motion, we should be able to solve this problem quite quickly. Okay, so vertically, it says momentum must be conserved. The equation for momentum is P equals mv. So initially, vertically, the total momentum was 0. Yeah. Now, how you get the marks we'll go through later on, but this is the underlying theory. So resolving vertically, initially the momentum is 0, so I've put that the total momentum before was 0, yeah, should equal the total momentum after. Now, interestingly, the mass is the same for both, so you can actually cancel out the masses, and you come up with the following algebra. The m times 0.87 sine of 50, so we're going away from the 50 degrees. So the way I always explain to my students, if you're going away from the angle given, so you want to go rather than come into the horizontal component, you're going away from the angle given, which is to the horizontal. In other words, you want the vertical. You're going to go away from it. It's going to be 0.87 times sine 50. If you can't work that out, you should draw the triangle where you'd enable you to work out using SOHCAHTOA. Okay? So both of them are going to be sine, and in this case, mv sine 30. Yeah? So exactly the same. You're going away from the 30 degrees. Yeah? So it would be cos of 60 if you want. Okay? As long as you know how to do resolving, you should be fine with questions like this. Okay? So resolving vertically, changing the subject formula, dividing both all the terms by m means you can just ignore the maths, and it makes it quicker to do your calculation. So then V is the subject, yeah? Remember, there'll be a negative sign because the value downwards will count as being negative. It will give you an answer of 1.33 meters per second, which is approximately equal to the 1.3 that they want us to show it is. So this is how you should show your answers. Put it to 2 decimal places and then show that it's equal to 1 decimal place to about 1.3. Okay? So that's how you get your answer to this question. They actually give 1 mark for being able to use this equation. So for example, you say you've got the first one right, but you get the second one wrong, they'll still give you a mark for showing that you knew you had to use the momentum equation. The second mark, it's understanding that you have to take a component of the momentum. So as long as you have shown that you have done this correctly, for example, that you have used the trigonometric function for the x or the y components. Well, we did the y component because y is vertical. Then you get a second mark for doing the resolving vertically, yeah? And then you've applied the conservation of momentum, yeah? Where 0 is equal to the sum of the momenta, yeah? I should have really put this is by the conservation of momentum, and that would be something that I would add if I was writing it out again. And then you get 1 for getting your answer and for making a valid conclusion, which it is down the page, and approximately equal to 1.3. Okay? That's where you get your 4 marks for. Okay? Yes, I think that concludes it. And then going into the next part of the question, they now want to test you, and these are often combined together. Once you've done conservation of momentum, they want you to think about whether the collision is elastic or not. They want you to know, do you know what elastic collision means? So this question is asking you, deduce whether the collision was elastic. Show your answers. Your answers should include a calculation. So you've got to work out the kinetic energy before and the kinetic energy after. And then you'll see if they're the same. If they're not the same, then the collision is not elastic. So when you put the values in, yeah, there's only one object which is moving initially, half m times v squared. So m, let's just put the value in for m because it's given to us as 19.1 kilograms. So 19.1 times the velocity of the stone, which was 1.7 squared. When you put the answers in, you'll get 27.6 joules. That's the kinetic energy before. You then do the same. This time you're going to have 2 kinetic energies. You've worked out the velocity of the second one. Again, it's half times 19.1 times, in this case it's gone down, the first one has gone down to 0.87, square that, add it to the kinetic energy of the second stone, which is half again times 19.1, remember they've all got the same mass, multiplied by the value you worked out, and I would put the accurate value, 1.33, and square that. When you work out the kinetic energy afterwards, it'll be 7.2 joules, 7.2 plus 16.9, which gives you a total of 24.1 joules. So now, before it was 27.6, after the total kinetic energy was 24.1, so we've lost approximately 3.5 joules of energy, which is significant. So it is not elastic. Okay? The collision is not elastic. And that's where you get your marks from. One is using your equations to work out kinetic energy. Yeah? As long as you got one kinetic energy correct, you will get 1 mark. If you got them both correct, you'll get 2 marks, and then the comparison of the values and making a valid conclusion for your 3rd mark. I hope that's clear. So we can now move on to the next question, which is about electric fields. So, just straighten the page for you. So in the 18th century, it says a scientist called Gordon, not someone I've heard of, made the first device that used electrostatic forces to produce continuous motion. Okay, it's just a scenario. It's not something you need to have studied, but it's something you need to be able to apply your understanding to. A demonstration of the principle of Gordon's device is shown. A light conducting sphere, so they're telling us what's happening in a diagram. A light conducting sphere, so the conducting sphere is labeled. I always like to make sure that the words in the statement match the diagram so I can internalize the problem in my mind. Okay, is suspended from an insulating thread. So it's insulating means it's not losing charge through the thread. It's an insulating thread between 2 parallel plates, here and here. And you can see that they are charged by the battery. Okay, a large potential difference is applied between the plates. Okay, so this will be the positive plate, this will be the negative plate, because if you remember from Unit 2 or from GCSE, the big line of the battery is the positive, the small line is the negative. Okay, so once we know what the question is about, don't get scared by reading a lot of text. It's just making sure you know how you need to apply the problem. Okay, and then it says there is an electrostatic force on the sphere, because it's a conducting sphere, so it will feel the force. Any object will feel an electrostatic field. So when you rub a balloon on your hair, you can feel it, the effect on your hair. The charged balloon attracts your hair. There is an electrostatic force on the sphere when the sphere is charged. Okay, so it's not initially charged, but it will be attracted, or it will move possibly to one side or the other. The capacitance C of the sphere is given by this equation: C equals 4 pi epsilon naught r. Now, this 4 pi epsilon naught r should be familiar to you as being very similar to an equation you've used in studying this topic. Now, remember also that charge is equal to CV. It's just the general rule for capacitance. Okay, so we know the capacitance. We don't know any more information yet, but now let's see what they're telling us. Where r is the radius of the sphere, okay, so r is the radius of the sphere, and the sphere is charged by touching it onto one of the plates. So the sphere becomes charged when it touches one of the plates. Doesn't matter which plate. The plates are a distance d apart. Okay, so if we know the plates are d apart, and if they give us the voltage, which they have, then you also know the electric field strength is equal to V over D. They want you to calculate the electrostatic force exerted on the sphere, in this situation. So the voltage is given as 4,500. The distance is given as 5 centimeters between the 2 plates. So that will enable us to work out the electric field strength. We also know they're given us the radius of the sphere, so it allows us to work out the capacitance of the sphere. So, how do you answer this question? Well, these are my steps. The first thing I would do, is to work out the electric field strength. So you just divide the 4,500 by the separation, making sure you put 10 to the minus 2 centimeters into meters, and you'll get the electric field strength either in volts per meter, which is voltage divided by distance, which is also equal to newtons per coulomb. Okay, So once you get that electric field strength, it will come out to 9.0 times 10 to the 4. Okay? That's the electric field strength. Now, once you know the electric field strength, it will enable you to move forward. When the sphere of capacitance C, given by this equation up here, touches one of the plates, it gets charged, as they told us. Where Q is equal to CV, as I've already explained to you. So you multiply the capacitance, which is 4 pi epsilon r, by 4,500. Yeah? You put in the numbers for epsilon naught, which is given to you in a data sheet. There's epsilon naught. 4 pi you multiply. R is the radius in centimeters converted by multiplied by 10 to the minus 2, change from centimeters to meters, multiplied by 4,500. That will enable you to work out the charge. Okay, so you already will get 1 mark for getting the capacitance. Yeah, you get 1 mark for that, and you'll probably get 1 mark for working out the charge as well. And the charge comes to 1.75 times 10 to the minus 8 coulombs. Don't forget to put your units in, even in your interim measures. Now this will give you a 2nd mark. Now I've gone straight into working out the charge, but you would, if you just worked out the capacitance first, you'd get 1 mark for working out the capacitance. I just feel in the exam, if you take shortcuts to save you time, it gives you more time to finish the paper if you're under pressure. When this happens, a force is exerted between now the charge sphere and the charge plates. And the force, which I put up here, is equal to the charge multiplied by the electric field. So you've got an electric field between the plates, you've got a charged object in there, it feels a force, and this is the equation for the force on the charge. And once you put F equals QE into the numbers, so we have the E, you basically are multiplying this number by this number. So you're multiplying this number by this number. And when you multiply those two by each other, I'm not going to write it out because of a shortage of space, you should get the answer of 1.58 times 10 to the minus 3. Don't forget the units, newtons. Okay? Now, then, I'm sorry, I was too far away. So let me just go through that again. So initially, you work out the electric field strength. You get 9 times 10 to the 4 volts per meter. And then using the equation for capacitance and charge, you can go straight into charge, multiply all the values out, 4 pi epsilon naught r. There's epsilon naught from the data sheet. There's the radius in meters. Yes, given to you in centimeters here, you must make sure you convert to the meter, multiply by voltage, you get straight into the charge of 1.75 times 10 to the minus 8 coulombs. Yeah, you get 2 marks for this, 1 for knowing how to work out the capacitance, and we've done it all in 1 step and gone straight into charge. Okay, which is what I was explaining before. Apologies for not having my screen showing the correct part of the page. When this happens, the force is exerted, F equals QE. Yeah, this is a known equation. Yeah, and then you multiply this number by this number, you'll come up with 1.58 times 10 to the minus 3 newtons. Okay, so now the next question wants you to analyze what's happening a little bit further. Okay, so over the page is a 3-mark question. Explain why. It wants you to explain why. Let's have a read. After the sphere has been charged, the sphere start to oscillate between the plates. Okay, well, because if it gets charged by one of the plates, it will get the same charge as the plate it touches. So then it's a repulsion force, so it'll push it towards the other plate. The sphere touches each plate alternately, gets charged the same as the plate it's touching, be repelled, so that's what causes it to oscillate. Okay, so basically transferring charge from one plate to the other. Explain why the conducting sphere oscillates between the two plates. Well, I've already explained it to you, and this is how I'm going to read it out to you. And again, I will put it in the next video, written out, so you have time to stop the video and listen to what I'm reading. Okay, so when the sphere touches the plate, it is charged with the same polarity. The force on the sphere due to the electric field is a repulsion force away from the plate, so that it moves towards the oppositely charged plate. Okay? Or you could have said the sphere is repelled from the plate with the charge of the same sign. So rather than use the word polarity, as long as you get the concept that there is a repulsion force involved, you will get 1 mark. Okay? You could also say the sphere is attracted towards the plate with the opposite charge. When the sphere touches the plate opposite the first, it becomes oppositely charged, and then it will be repelled again from the charged plate, and so on. So this keeps on repeating itself. When the spheres, this is another way of getting the answer in terms that will give you a credit for it. When the spheres touch the oppositely charged plate, it becomes oppositely charged and is attracted to the first plate. So that's what the oscillation means, that this is a repeated process of getting charged one way, then the other way, and therefore repelled from one side, attracted to the other side, and so on. So they want you to break it down to 3 marks. Okay? Those answers are from the mark scheme. Okay. As I said, in the next video, I will put this out in writing so you can look at it in the next video. Okay. Now, part C, we're just going to make sure we finish this question. It's a long question. It's a 10-mark question, but there's a lot of reading involved. So going to the next question. Part C. A few years later, another scientist called Franklin adopted Gordon's device. Franklin suspended a conducting sphere, same as before, between 2 metal balls. Okay, one metal ball was connected to Earth. You can see that this metal ball, this metal bell, I said ball, was conducted to a lightning conductor. Yeah, on the other side. So here's a lightning conductor. So the lightning conductor will kind of be a charge. So this side will get charged. Earth is always neutral. Okay? So you have a neutral voltage, 0 voltage. Earth is always 0 volts. And this will be high voltage. Okay? Now, it doesn't really matter whether it's positive or negative. That during an electric storm, it says the sphere oscillates between the bells and the bells ring. Okay? So when there's a lightning coming, this device will feel the charge in the atmosphere and will behave like the example on the page before. So it says a lightning conductor is a long wire attached to the top of a building. Okay, so here we're in Dubai. We have the tallest building in the world. They actually have a lightning detector, a lightning rod, which collects the charge and dissipates the charge down to Earth to neutralize it and stop it going through the building. The lightning conductor becomes positively charged when in an electric field. They're just telling us that. I don't think that's always true. Yeah, from my understanding, the bottom of clouds are often negatively charged, but I'm not an expert on lightning. The conducting sphere is initially uncharged. Okay? Sorry about the camera seat keeps going out of focus when I oscillate the table. Explain why the conducting sphere starts to move between the bells during electric storm. Okay? So, the way that you need to answer this is as follows. The bell connected to the lightning conductor becomes positively charged as explained in the question. So, electrons are attracted to the right side of the sphere. Electrons are attracted to the right side of the sphere. So if this is positive, the electrons on this side will be pulled to this side of the sphere. So this side of the sphere becomes negatively charged. Yeah? So separation of charge. This side will be positively charged. Yeah? So it's basically electrons will flow to that side and repelled from this side. So when that happens, you're going to have an attraction between the two. Does that make sense? Waiting for my autofocus to come back together. So that's the first mark, is that you realize that electrons are collecting on the right side of the conducting sphere. The sphere is then attracted to the positively charged bell. And that's basically all you've got to say for the 2 marks. And that is the end of this video. I just want to go back. I hope that makes sense. I just want to go back to a question from the previous video where I promised you I would show you the Lenz's law, and this is the PQ that's going through the magnetic field in question 17. Those are my written responses, yeah, where I explain that 1 mark for explaining Lenz's law, 1 mark for explaining that the force is against the motion, and 1 mark for working out, for example, using Fleming's right-hand rule, that the EMF must be from P to Q to produce this opposition. So this is the end of the next video. I hope you found it useful. Once again, like it, please, if you can, share it with your friends so we get more visibility and it enables us to make more videos, and subscribe if you'd like to know when the next video is ready. Well, the next question that we'll come to will be question 21. Okay? So I look forward to seeing you in the next video. Thank you very much.